This video is about linear approximation. That's where you use a linear function to estimate the value of the actual function close to the point of tangency. But before we get into that, we need to do a brief review of how linear equations work. Now, back in middle school, the first thing you probably learned was y equals mx plus b. This was slope-intercept form, because in order to write an equation, all you needed was a slope, like let's say the slope is 1/4, and the y-intercept, let's say 0, 3. If you had that information, you could write an equation like y equals 1/4 x plus 3. Boom. And that got us pretty far. But hopefully by the time you hit pre-calculus, they introduced you to point-slope form, which is actually more useful because we still need the slope, but the point can be any random point on the function. Instead of a more special point called the y-intercept, it could be any point. So that makes this a lot more useful. So given this information, according to point-slope form, I can immediately write an equation that would go y minus 3, right, is equal to 1/4, and then x minus 2. Boom, we have an equation of a line. So this is what we're going to be using in a calculus class much more often than any y equals mx plus b. So one more thing, if I were to get y by itself, I could easily add y1 to both sides, and this standard equation would simply become y equals y1 plus m times x minus x1. But you can see that these are the same thing. But for what we're going to do next, this is the version that I want you to focus on. So here it comes, tangent line approximation. The equation of the line tangent to f of x at the point c comma f at c is this, y equals f at c plus f prime at c times x minus c. Now quick, look back at our point-slope form. I want you to see that these are the same thing. So the point of tangency, c comma f at c, is just another way of describing a single point that we're given. This is now standing in for x1 and y1. So this equation, this point-slope form, you can see that x1 is c. So that's why there's a c there. And the y1, that's the f at c part, that's the y value. So that's why f at c is ending up right here where y1 is. And then we have m, the slope. But in a calculus class, we have drilled into our heads that the derivative is the slope. That's what derivative is. It's the slope of a curve at a point. So of course, instead of an m, we're going to have f prime. So all this is y equals the y value of the point of tangency plus the slope, and then x minus the x value of the point of tangency. But if you look at it that way, you can see that it's just point-slope form. That's all it is. So that is the tangent line approximation. It is also called the linear approximation of f at c. So this kind of approximation only works well when you are close to the point of tangency. In fact, by choosing values of x sufficiently close to c, the y value can be made arbitrarily close to f at c. Let's go ahead and look at an example. So, example 1, find the tangent line approximation of f of x equals 1 plus sine x at the point 0, 1. Then use a table to compare the y values of the linear function with those of f of x. So tangent line approximation. We are going to be using the point of tangency, so they're giving us the 0, 1. So understand the point of tangency in the formula that we just used we have C and f at C, and they're telling us that that is the point 0, 1. So C is 0 and f at C is 1. Our formula involves f prime. So we're going to need the derivative of this function. So let's go ahead and get that down. F prime. So the derivative of the constant is 0, and then the derivative of sine x is cosine x. So that's it. That's the derivative of f of x. So now we can go ahead and set up the equation of the tangent line, which is going to be y equals the y value, f at c, plus the slope, which is f prime at c, and then times x minus the x value, which is c. So I've just recopied the formula. But now I'm going to substitute in everything that we just found. So this will be y equals, and then f at c is 1, so I'm going to have a 1, plus f prime at c. Well, f prime is cosine, and then the c value is 0, so that's going to become cosine of 0. And then I'm going to have x minus c, but again, c is 0, so that'll be x minus 0. So let's simplify this. Cosine of 0, of course, you should be able to automatically know what that is. But just in case, you're feeling sleepy or something, remember that cosine is the x value on the unit circle. So the cosine of 0 is 1. That's the x value at 0. So we're going to have y equals 1 plus 1 times x minus 0. But that's just going to be y equals 1 plus x. So this is the equation of the tangent line at the point 0, 1. Or we could call this the linear approximation of f at 0. Remember, 0 is the point of tangency. Let's go ahead and compare the linear approximation to the actual function and see how those values line up. So the top two rows are the x values and then the values, the actual values of the function. The third row is our linear approximation. Notice that at the point of tangency, which is the 0, 1, the approximation is exactly right. All right, our 1 plus x approximation gives us the same exact value. But as we move a little bit away from the point of tangency, so instead of 0, we're talking about 0.01. So the actual value of the function at 0.01 is this, and our linear approximation is giving us this. Notice how close these are. If you're going out to 2 decimal places, they would round to be the same thing. As you go a little bit further away, okay, at 0.1, the value of the function is this, 1.0998. But then our approximation gives us 1.1. Still very close, not quite as close as the previous, but still very close. Even if you go all the way out to a half a unit away, the actual value of the function and our linear approximation, the 1 plus x, is still giving us a value that's pretty darn close to the real function. So as long as we're staying fairly close to the point of tangency, this straight line is going to give us a value that's pretty close to the real value. If you glance at a graph, you can see why this is working out so well. Close to the point of tangency, you see that the function and the linear approximation appear to overlap. So as long as we are near the point of tangency, we can often use the linear approximation as a substitute for the actual function.